Okay, so this time, now we might want to we might want to go, well, this seems like a little bit more of a difficult process, and I'm going to actually compare this to a different way of finding a slope of this line tangent to a curve. I'd like you to note, first of all, that in this circle, we know exactly what happens at every point. We don't even really need any fancy calculus to tell us what the slope of a line tangent is here, and I will show you why. Let me just draw in just a thinner line right here just to illustrate it. If I were to draw a line from the center of a circle out through this, I will tell you that that line that comes from the center of the circle to the point xy is perpendicular, always perpendicular to the always perpendicular to the line that's tangent to the curve. That's our one of our rules from geometry. And so what could we say about it? Well, sort of the interesting thing that we could say about this particular line is that we know how to get its slope right away, right? Here's 0, 0. Here's the point xy. So if we were really interested, we might say, well, okay, the slope of this line, that is uh, going from the center through the tangent line, the slope of this line right here is equal to the difference in the y values, y minus 0, over the difference in the x values, so that's x minus 0, right? And so the slope is y over x. And so you might say, well, okay, what is the slope of the line perpendicular to that? And that perpendicular line, by the way, is the tangent line. Well, perpendicular line is the negative reciprocal of the other tangent line, so the perpendicular should be negative x over y, right? So whatever xy point we picked, that as long as it's on the circle right here, this property is always true. So now we actually have something to check this against when we take our derivative right here. So now let's go through the process. Let's use the implicit differentiation method to find the derivative of x squared plus y squared equals 4. That is this equation of the circle tangent to the line at xy. And compare. So what should we get? Well, if we do the implicit differentiation method, that means we're going to take the derivative with respect to x of both terms on the left. So we're going to take the derivative with respect to x of x squared plus the derivative with respect to x of y squared, and that will be equal to the derivative with respect to x of 4, the radius. So when we do that, well, take our derivative on both sides here. We're going to have 2x plus, and then we're going to take the derivative with respect to x of y squared, and I'll explain this one in a minute. And we're going to set that equal to the derivative with respect to x of 4. We know that's 0. So what do I do with this business right here? Well, if you recall your chain rule, we're actually going to use that general chain rule, right? We would have said in the general chain rule that if we took the derivative with respect to x of u raised to the nth power, then its derivative would be n times u to the n minus 1th power times the derivative of u with respect to x, right? And this would be our chain rule that we discussed in the last section. So let's use our chain rule right here. Our chain rule would tell me, well, if I take the derivative with respect to x of y squared, I treat y just like I would treat u. Y is implied to be some function of x, so I could say, well, it's 2x plus 2y to the first, subtract 1 from the exponent, times the derivative of y with respect to x. So now let's go ahead. We want to solve for dy dx. I don't even need to carry this 1 right here. I can say, well, if I subtracted 2x from both sides, I would have found that 2 times y times dy dx is equal to negative 2x, and hopefully you can already see where this is going. Dy dx would be negative 2x divided by 2y, And yeah, sure enough, dy dx, the slope of the line tangent to the curve at any point xy is equal to negative x divided by y, just like we said it should be. So this is our differentiation method for implicit differentials. Remembering that we use this chain rule to help us with certain parts of this differentiation right here. More to come.